Okay, next chapter is 3.75. There I want to discuss the PD, two blocks in the same chapter, PD and the PDT1 block. I can do this in one chapter because the PD block is a special case of the PDT1 block. I would like to start with a circuit. Again, operational amplifier circuit. Ideal operational amplifier, inverting amplifier as a basic circuit is used, but now output voltage is unchanged as done before. Positive input is grounded, negative input is connected to two impedances. The input voltage U1 is connected via an R1 directly to the negative input, and the feedback resistance is again a resistance, and the difference to just a simple P is that here parallel to the input resistance we find a third resistance in series connection with a capacitance. So this is a capacitor C, and this is the third resistance called R sub 3. Okay, first we calculate the transfer function of the circuit, and then I can show you that this is the transfer function of a PDT1. Can be found in the workbook, page 16. The transfer function is calculated by feedback resistance. It's just simple the R2 divided by the input resistance, input impedance. In the input we have a parallel connection of this R3 in series with C parallel to R1. So we use the parallel circuit equation. In the numerator of this parallel circuit division line we see the product of the parallel impedances, that is R1 multiplied with the series connection of R3 plus 1 over PC. Quantity closed, division 9 enlarged, and in the denominator of the denominator I write the sum of all the impedances, and now we have to convert this in a better form. So first we see that there is an R2 divided by R1. I can shift into the front. Then we have a division line, and here the ratio in the denominator can be converted into the ratio on the numerator by multiplying both parts here with the denominator of the denominator. Then this goes up into the numerator and this stays in the denominator. So we have here an R3 plus 1 divided by PC, and here we copy the R1 plus R3 plus 1 divided by PC, and the last step is just simple f of p is numerator and denominator multiplied with PC. Then we have the unchanged prefactor multiplied with 1 plus PC times the sum of R1 plus R3, and the denominator 1 plus PC times R3. Okay, you see In general, we can say the prefactor is the ratio of two resistances. It's a real number that is a k value. Then we have two 1 plus pt terms, 1 plus pt in the numerator and a 1 plus pt in the denominator. Let's call this that is a numerator time constant, c times the sum of both resistances. In our writing, this is called a differentiating time constant, and in the denominator we have just a simple time constant with a running number t1. We can have a quick look into the workbook. The workbook is on page 16 what we can find in the PDT1 case. In the workbook on page 16 in the table we have to look in the both rows 11 and 12. Here is the PDT1, here is the PD. Look into the PDT1 and you see this transfer function is exactly that what we have just calculated from our circuit. There is a k and then a 1 plus pt term in the numerator and a 1 plus t1 term in the denominator. The PD is different to this, and you see the PD is just only the numerator. The denominator is just 1 or gone, or we can say T1 is 0. Yeah? If T1 is 0, the PDT1 converges to the PD. That's the case. Yeah? So we can cover the PD by just simple the special case that T1 is 0. Okay, so warte mal, hier weg. So. Okay, so in green I want to add now a special case situation, special case PD. We can say, okay, if T1, which is, what is T1? Yeah, we have to indicate the time constants. Sorry, I have to just switch back to black. This product we have called T1, and the numerator time constant is TD. You can see the T1 is just the product of the capacitance C multiplied with R3. So the special case is if this is 0, of course C cannot be 0. If C is 0, then we have a simple P block. So this is not so interesting. But if R3 is 0, this has no influence to TD, because TD then is in a remaining product C times R1. So R3 0 means now we have no resistance here. We can say in the short circuit between over R3. And we have just a simple parallel circuit of R1 with C. In this case, then the transfer function, you can say the PD of P is K multiplied with 1 plus P TD, and TD in this case is just C times R1. Okay, we will add special case information for the PD block in a relevant subchapter, so I switch back to black color and I continue with the step response. Step response. Again, U1 is the step function and U2 is the step function multiplied with transfer function, and the transfer function then is just a copy of that what I have done before, divided by 1 plus PT1. Yeah, and if we look into my Laplace table, I have to look for term which has a first order function in the numerator and a p times p second order function in the denominator. So I have to go to that section which starts in the left column with the numbers 1 dot 2 dot. So look into the section of the workbook. There are many lines with starting 1 point dot. So 1 dot 2 dot. So we have look which structure is fitting. We have, and you see, we have a 1 plus pt term in the numerator and a p times 1 plus pt term in the denominator. So at once you can stop here looking for the best fit, because 1 dot 2 dot b is the correct line. I make a copy of this line into my OneNote, then we can work with this. Yeah, I have copied this line 1 dot 2 dot b, so we can here write a b. Then we make a coefficient comparison. My application 3.7.5 and table has different names for same parameters. First, both sides have to be multiplied with a constant factor u sub o times k. Then what I have called td in the table is called s, and what I have called t1 in the table is just simple a t. So this is a replacement, the coefficient comparison, we can say. And then with this knowledge we can just write down the step response time function, which is an prefactor multiplied with this function. This function is a 1 plus s is td, is td minus t is t1 minus t1 divided by t1 multiplied with e to the power of minus t divided by, here's a t, this t is t1, so this is t1, parenthesis closed. And this is a function which is a step response of my PDT1 block. We will do the green special case later. First we try to discuss this curve a little bit. u2 of 0 starting value and u2 of infinite final value is helpful to draw the function. If t is 0, this becomes a 1, and then we have to add the 1 plus this term and multiply with this element. So the result is u sub ok multiplied with the result of this calculation, if this is 1. This 1 has to be expanded to a denominator of t1. So we have a positive t1 here plus td minus t1 here. So the final result is td divided by t1. Now I would like to introduce a new parameter. The ratio td over t1 is in the next steps in my lecture is called step depth. New parameter, because this parameter is helpful in understanding the function. New parameter, the ratio of the numerator time constant divided by the denominator time constant is called st, and this is called step depth. Why this name step depth appears here in this position we cannot understand at now, but later if I discuss the Bode plot of this circuit, then I can show you why this name step depth is a good name. So we can say, okay, the starting value is u sub o times k times step depth. Okay, the final value is simple, because then this exponential function for large t's with negative exponent is 0, so this is 0, and here in the quantity remains a 1, and we can say final value is u sub o k. This leads to the following diagram. step response diagram over t, and here we have u2 of t. And we can say, okay, the question is the step depth larger than 1 or smaller than 1? Which value is larger, td or t1? We have just in our circuit, we can just very quickly decide this, because td is r1 plus r3 times c, and t1 is r3 times c, so this must be larger. So in this case, step depth is larger than 1, and that means the starting value here is with step depth larger than final value. So in our drawing we can say, okay, this should be final value, u sub ok, and starting value is u sub ok step depth. So, and we know, okay, this exponential function settles at final value, start at 0, make an impulse at the beginning, a strong, very quick impulse function to this amplitude, and then this exponential function defines the connection from this point to the final value. This can be drawn with the tangent construction. So define a tangent from the starting point to the cross point with the final value. This time again is our exponent time here in this exponential function. I think this is a knowledge which comes out other lectures. You have seen this, I think, several times before. So with this tangent construction, we can draw now the exponential change from the starting point to the final value for this curve. So we see the step response of a PDT1 has a strong impulse here. The impulse length is defined a little bit with the T1, goes exponentially down to the final value. And this is a typical curve which defines the symbol of the PDT1. This symbol of the PDT1 gets the symbolized step response. So we have here a curve which ends up not in the corner. There is another block which ends up in the corner, which is a DT1 without the P. This should not mix this up with a pure DT1 block. Then on the top left corner we can find K. Now we have a small problem, because now the transfer function carries now 3 parameters, the K, the TD and the T1. So we need 3 corners, but we have only 2. So the solution is write the time constants just in one after the other on the top left side. Some people also write this time constants in a vertical way. Both is possible. It's not clearly defined. So this is a PDT1. Now I switch to green case. What happens in the green case? R3 is 0, T1 is 0. That means, okay, what happens here with the step response? The step response ST is a ratio TD over T1. If the denominator goes to 0, the ratio goes to infinity. So we can say step depths will be very, very large, infinitely large. That means this impulse length goes to 0 and the impulse amplitude goes to infinity. So we have here in the PD case a Dirac impulse in the beginning. So the step response drawing looks like this. We have just u2 of t green case starting with 0, then impulse function with this arrow which indicates that is a Dirac impulse. Yeah. Dirac impulse, ending with the unchanged U sub OK here. And the area, yeah, just is, how large is the area? No? The area is Dirac impulse is U sub OK, yeah? The area of this Dirac impulse. But you see, again, if step response carries a Dirac impulse, we have to be careful in simulations or in calculations and predictions with mathematical equations. If the input of the circuit jumps like a step function output, had theoretically a Dirac impulse, in lab, in real measurements, of course not. And then we have a big difference between theory and measurement, and that's what we don't like to have. So be careful in PD case with step functions at the input, then the output differs between theory and measurement. There is a symbol for the PD. You've seen in the workbook, the symbol symbolize the step function. We have here a K and here a TD. This symbol can be mixed up with a D block. Yeah? If you go back to the D block, where is the D block? Here. The display is very similar. The only difference is the distance from this line to the bottom line. So it sometimes is helpful to have a clear difference between those symbols. Yeah? An automatic reading program don't like to have this. So some people add now a line here in this position, then this is a clear difference between a PD and a pure D. Yeah? That is the PD block. Another clear difference is the second number on the top right corner. Of course, if there is a number, then this must be a PD, because a pure D has only one number on the top left side. Okay, I want to add now the discussion by changing step depth values to show you that PD could also have step depth values which are smaller than 1, or could be 1 or could be negative. Yeah. Let's make a table. Variation should be black. Variation of step depths. Then you can see the step depth value is a very powerful parameter, because now with changing of the step depth you get different types of functions. Yeah? Type. Let's start with infinity. Then the PD variation type of PDT1. Yeah? PDT1. If step depth goes to infinity, we have seen the type changes to a PD block. If step depth is larger 1, this is a PDT1. In Germany, we don't differ between step depth values larger and smaller 1. We will look what happens if step depth is equal 1. Now this is step depth between 0 and 1, and then the step depth could also 0, and the step depth could be negative, smaller than 0. In Germany, in Europe, in both cases we call this block, independent of the size of the step depth, PDT1. In US literature, this has another name. This is a lead block, from leading phase, a lead block. and this is a lag block. From lag phase, this is negative phase. Yeah. So in the USR literature, there is a different name between step depth larger one and step depth smaller one. In Germany, not. What happens if step depth is 1? That is very simple. If step depth is, the definition of the step depth is the ratio. Where is it? The ratio of the time constants is here, Td over T1, that is step depth. If step depth is 1, it's not possible with this circuit, but it is possible in other circuits. If the numerator time constant is equal to the denominator time constant, then this expression and this expression is the same. We can extract it, and we have just a constant factor here. So the special case step depth 1 is just a simple P block. Here we should draw the step response. It looks a little bit different. U2 in the lag case, the starting value is smaller than ending value. So we have here a value U sub OK, then a tangent construction, again T1 as a time constant, and then an exponential function which ends up in the final value. Now the final value is of course the same, but now the starting value is U sub O times K times step depth. If step depth is small, between 0 and 1, starting value starts of course with a smaller value than the final value, then this goes up. Now this is a case of step depth smaller than 1 but positive. Step depth 0 is also a case. What happens with step depth 0? Let's look. The step depth 0 means Td 0. If Td is 0, we have a function here. If this is 0, it's k divided by 1 plus Pt1, and that is a well-known block function which we called Pt1. So the differentiator is gone, Pt1. And to have a complete list, negative step ones are not clearly defined. There's one special negative value, not negative values. One special negative value is step depth is -1. Then we call this an impasse. But it is a very unimportant block function in our control system theory, so forget it. But I think with the complete list I should note that there is also a possibility then the step function starts with negative value and goes up to positive value. Forget it, not so important. Here the most important PDT1 is here, the step depth larger 1. If step depth is larger 1, this is a good controller for special cases. Controller, especially if the system is unstable with PDT1, you could stabilize the situation of a PDT1. Last question before I add the Bode plot in the next video is: can we realize step depth value smaller than 1 with this circuit? Now I have introduced a PDT1 block with this circuit. You see here always the numerator time constant is larger than the denominator, because here the sum has in R1 more, so Td is larger than T1, so step depth is always larger 1. So with this circuit, a step depth value smaller than 1 is not possible, but I can show you very easily the circuit can be changed into a circuit where this is possible. Circuit. We need a circuit where the denominator has a larger time constant than the numerator, and this is possible with the following circuit. The change is rather extremely easy, because we know, okay, the transfer function of an inverting amplifier is the ratio of the impedances of feedback divided by input impedance. So this is the circuit, ideal operation amplifier. The step depth value larger one gives this RC combination parallel to R1. And if I exchange this to the parallel circuit of RC in the feedback branch, then the time constant T1 and TD exchanges position. Now I exchange just the Z1 with the Z2 with the Z1. Then, of course, in the denominator I have the larger time constant. So this is the case where this 0 is smaller than step depth is smaller than 1. So if we need a circuit where we have step depth values smaller than 1, we have to change the circuit to this situation. Okay, next video, some words to the Bode plot and some words to the application possibilities of a PDT1.